So I'd like to thank everyone for taking some time out of your day to join us to learn a little bit about the North American Eagle project that's attempting to break the land speed record. And again, we're here specifically to talk about how they're using CFD to help them achieve that goal. So with me today, we have Darren Grove as the participating member of the NEA team, who's an aerodynamicist that's helping them with that part of it. A little bit about Darren. He holds a BS in aerospace engineering from the University of Maryland and an MS in aerospace engineering from Naval Postgraduate School. You can see that Darren has a couple decades of experience with CFD and fluid dynamics and aerodynamics on a variety of different aircraft projects, military to commercial, and currently is an aerodynamicist within the Boeing Commercial Aircraft Company in Washington. Also joining me from Computational Engineering International is Kevin Colburn. Has been also has a pretty broad range in automotive, combustion, aerospace background, and as well as CFD. He's been with Insight for several years now, and anyway, so he's here to talk a little bit about how Insight was used for this NAE project. And then myself, I've been hosting these webinars now for a couple of years. Again, my background is fairly broad. I have a BS and MS, and also a PhD in mechanical and aerospace engineering. Worked in a variety of different capacities prior to my my employment here at Pointwise. So a little bit about our agenda. So we're going to talk a little bit about some background and motivation for the work today. That's what Darren's going to touch on. Then kind of the process of what we're going to describe today is maybe similar to how you would actually do the CFD process, where you would do some pre-processing. You would run the calculation, look at your results, try to do some sort of analysis, and then Kevin's going to jump in and talk about how Insight was used to help automate and diagnose some of the aerodynamic information that was generated. So obviously a big concern with the NEA project is the challenges of designing a supersonic ground vehicle, considering this has only ever been done once in history before, breaking the speed of sound with a ground vehicle. And then how they were able to use CFD as an efficient tool to do that. And I won't steal any of his thunder here. I'll let him talk about that in more detail. And then Kevin, like I mentioned, is going to jump in and describe how Darren was using Insight for the post-processing duties. So on the front end, on the pre-processing end, I'm going to speak a little bit about robustness and pre-processing and how Pointwise can help you achieve that. So what do I mean by robust pre-processing? So here I'm going to equate robustness to flexibility, and the flexibility in Pointwise can be achieved in several ways. And so here I have just kind of the four core categories that we generally refer to. So one is where does your CAD come from, and how is it imported, and how do you deal with it once it gets in? Different formats, different cleanliness, all sorts of different sources. Also meshing strategies. You can choose a variety of different meshing strategies depending on how much time you have, how much computational resources you have at your disposal, the level of fidelity that you're interested in, and how your solver performs in those different mesh types. I mentioned performance. It's nice to be able to do this stuff really quickly so that you don't have to wait forever for the mesh if you're doing all sorts of different design studies. And then clearly getting your mesh out into your solver is pretty important, so I'll talk about that a little bit here in the next slide. So just more specifically in regards to what Darren was doing with the NEA project is, first of all, is we have some native CAD readers that allow you to import native CAD files. So in addition to IGES, you can import CATIA, Unigraphics, ProE, SolidWorks, and actually there's 8 total native CAD readers that you can use to bring in geometry. Darren was using our unstructured viscous meshing technique called T-Rex. We've had several webinars and tutorial and demonstration videos explaining how T-Rex works, so probably not going to get into a lot of detail about it, but again, it's a pretty powerful tool for doing quick, high quality viscous meshing. And then on the export side, Darren was using Metacomp CFD++, so You can directly export his mesh to CFD++, and then I'm going to describe a little bit about this prism recombination that I have up here. So here's just a nice little infographic, again, highlighting this robustness equals flexible. Again, I mentioned all the CAD formats on the left. There's a variety of different CAD formats. Getting your mesh out on the right-hand side, that's the getting out to all your solvers or whatever analysis tool you're using, if it's FEA or CFD or electromagnetics or whatever you want. We support 44 different CA solvers right now, and then if there's one that's not supported, we have a plug-in software development kit that allows you to write your own. Maybe you have a custom format or some specific needs, and then the two little bubbles above and below point-wise are just almost like side doors into the software. So the top is our glyph. It's our scripting language based on Tickle TK. So you can help yourself automate particular processes or the entire process. I think Darren's going to talk a little bit about how he used glyph for some of his work. And then on the bottom we have just some more neutral formats to get your geometry or mesh information into point-wise. So I mentioned the geometry handling before. Darren was using our native CAD import to bring in CATIA files, and really the goal of that is to help with the interoperability issues most people are familiar with in the CFD world. And then as a complement to that native CAD import, we have a solid meshing and quilting functionality, and that really the goal of that is to help you get to a meshing ready collection of surfaces quicker. So the images I have here are a good example of that. So on the left is the rendering of an early version of the NAE car that in CATIA you can see all these little patches all over the car, and this is just a product of CATIA, just its method for going ahead and create surfaces. But clearly these thousands of surfaces, which may or may not even be watertight, are probably unnecessary for a meshing process. So on the right we have this of the cleaned up geometry and point-wise, and you can see it's been just reduced to just a handful of surfaces on the fuselage and on the canopy and etc. So this is kind of where we want to go. So this is what the solid meshing and quilting helps help Darren achieve. I touched on the viscous meshing a little bit. T-Rex, again, we've talked a lot about this in the past. We have a lot of information on our website about T-Rex, but the goal of it is to help automate boundary layer meshing, using high aspect ratio tetrahedrons. And the reason for using tetrahedrons is that they're extremely flexible. They can handle extremely complex situations and collisions and all this kind of stuff. But T-Rex itself is again a fairly automated tool. There's just a few parameters you enter and away it goes and does its business. But if needed, there are a variety of different manual tools that kind of span the whole range of give you the ability to kind of modify the mesh. And so I'm just showing here the most manual method we have. You can actually tweak the location of individual grid points, and this is the case. It's sometimes just a handful of points that are causing you grief, maybe causing the solver convergence to stall. So this is the kind of range of flexibility you have in modifying the mesh and point-wise. And then the last one here is exporting a mesh. I mentioned Darren was using Metacomp CFD++, so you can export both the grid, the raw definition of the grid, as well as the associated boundary conditions, which can be specified in point-wise. You can export that directly to CFD++'s format. I mentioned a little earlier the prism recombination, so and as well as the fact that T-Rex itself just natively makes TETs only in the mesh, and so on the left panel you can see that the TET-only mesh that you would generate in point-wise has roughly 33 million cells. This is one of the meshes that Darren provided me that I could show to show here in the webinar. Now you can actually convert the boundary layer TETs, the T-Rex TETs, back into prisms, and so for every 3 of those high aspect ratio TETs you can recombine into a prism, and that actually happens on export. So you get a little box like this when you go to export the mesh. It says combine anisotropic tetrahedra, and then when it writes the file out, it in the message window it gives you some statistics of what happened. So in this case, the total mesh now has 15 million cells, so we've reduced the mesh count by 50 or 55%, and the bulk of our cells now are prisms in the boundary line. So this is great. This is what we want. We want these orthogonal faces. We have a better quality mesh, as well as we've reduced the size of the mesh. So with that, I'm going to turn things over to Darren and let him describe his work on the NEA project.
Thank you, Chris. So just to give you a brief, real quick synopsis of, I'll try to get my slides here working. I'll be touching base on the history of the car and how the North American Eagle became a reality, and then I'll go into some of the CFD aspects of what I've done so far with the car. Can't seem to advance the slides, Chris. My keyboard. All right.
I can go ahead and do it for if you want. Just let me know as you want to go.
Okay. So before I get started, though, I just have to have a conflict of interest statement here. I just want to say that although I am employed by the Boeing company, this project is not sponsored, funded, nor associated with the Boeing company. My work on this project is outside of the Boeing company on a volunteer basis, and also that the North American Eagle team is comprised of an all-volunteer team. So we, unfortunately, we don't have daily operations and day-to-day operations where we just work on the car and try to meet our goal. That's why it's taken us a little longer than to get the car out on the track and test it in the desert. Okay, so also wanted to say that some of the images, the CFD images and car geometries that you'll see in later slides will change. There's some old setups and then some new ones. But let's touch base on the history. So for over 100 years now, people have been pushing the limits of wheel-driven vehicles to higher and higher speeds. This chart shows the progression of increasing speed over the past 100 years. The lower left-hand side of the chart shows the early years with piston-type engines. Note in the early years from around 1910 to 1927, the speed of the car did not increase by much. But by 1930 to 1950, we see a steady increase in top speeds achieved. This was contributed by both the increased power of the engines and advances in the aerodynamic streamlining of the cars. In order to go even faster, though, using jet-powered cars were conceived and built starting in the 1960s. And in the years between 67 and 68, a car named Spirit of America was successful in reaching 600 miles per hour. This was quite an achievement because of the unknown risk could not be simulated with CFD at that time, and the cars were crossing into the transonic speeds where shocks were forming around the cars. The next 25 years saw only a few attempts to keep reaching higher speeds, mostly by the British, and in 1997 they were the first ones to break the sound barrier, reaching a top speed of 763 miles per hour. And so on the upper right-hand corner, you see the Thrust SSC car that achieved that milestone. All right. So here are some of the pictures of the previous land speed record holders in their cars. Note that the cars all have rubber tires. These special tires are good up to about 650 miles per hour. Any speed over this would shred the tires. So in order to achieve higher speeds, specially treated aluminum wheels are used. For the North American Eagle, we are using 34-inch diameter rear wheels that are designed to withstand rotational speeds up to 15,000 revolutions per minute. So what does it take to qualify for a land speed record? Well, in the lower left-hand corner of the chart is a diagram depicting a scenario. The car must start from one end of the lake bed, accelerate to a speed, and clocked over a distance of 1 mile near the halfway point right here. The car must then be turned around. Actually, after it comes to a stop, it's turned around and excuse me, prepped and completes another pass. So all this takes place within all this must take place within a 1-hour time frame, and the speed of the car is an average of the two passes. So our mission statement, well, we're here to we want to break the current 763 mile per hour world land speed record and our goal is to actually reach 800 miles per hour with the North American Eagle. So Ed Shadle, the man in the image on your left, is the owner, driver, and project manager. He is a former IBM manager specializing in disaster recovery computer systems for the Northwest region of the United States. After retiring from IBM in 1997, he formed his own company called North American Eagle, with the mission to bring back the world land speed record to North America, currently held by the British. Keith Zanghi, the man in the image on your right, is a co-owner and the director of operations. He is a former drag car racer, and his responsibilities include the project logistics and oversees the daily operations. These men, with a team of volunteers, work weekends trying to build the North American Eagle car to achieve its goal of bringing the land speed record back to America. So, bottom line, it's all in the physics. To make this project a success, we are challenged to adequately model the time, distance, and speed profile of the car that will go through. So this chart, as you can see, is a polar of that scenario. It will be critical to accurately model stages of the car's performance for predicting if we have enough dry lake bed distance to safely reach our land speed record and have enough distance to stop. So the profile is broken into 7 stages. Starting with the initial rollout, the engine will take some time to spool up. Then the pilot advances the throttle to accelerate to the maximum speed. And at the peak, the car needs to actually be going faster than the target. Remember, we are going for averages, and with when the pilot chops the throttle to idle, the car will decelerate quickly. After the pilot pulls the throttle to idle, it will then deploy the air brakes, followed by the parachutes, and then apply manual braking to come to a stop. A typical length of a good dry lake bed is on the order of about 10 miles for the dry lake beds that we test on. So the legacy continues. The North American Eagle car has a lot of history. The images above tell the story of how the once famous airplane that was used for testing at Edwards Air Force Base 50 years ago became the North American Eagle. The Eagle was born out of Ed Shadle and Keith Zanghi finding the old bird in a scrap pile at Edwards Air Force Base just prior to being melted down for recycling. Ed and Keith purchased the F-104 Starfighter from the Air Force and brought the plane home to Spanaway, Washington. In short, the wings were chopped off near the root and the suspension system retrofitted on the bottom of the airplane. The image in the lower right-hand corner shows the Eagle sitting on the dry lake bed in its almost current state of today. So building technologies. A few key technologies are being developed and built to support our mission. One is the electromagnetic braking system that you see pictured here on the right, and is needed to help stop the car in a short distance due to the finite length of the dry lake beds. Another is the aluminum wheels designed to withstand the enormous centrifugal forces due to extreme rotational speeds. Another critical feature is the parachute system that has a linear design to withstand the tensional forces up to a deployment of 700 miles per hour. Although I would feel sorry for the driver should he need to deploy it at that speed. I think our intentions are to deploy it down more around the 500 or 400 mile per hour mark. And of course, CFD is playing a major role in the design and optimization of the car aerodynamics. So the first step was to use advanced software scanning tools to construct a 3D model, a digitized 3D model of the car's features and using photogrammetrics. Then converted that data to a 3D solid model and read into pointwise to build the CFD mesh. Then we used Insight's Python scripting language to post-process many of the solutions in a meaningful way. So here are some of the things we're looking at, and some of the challenges that we're considering is vehicle-ground aerodynamic interactions. Typically a fighter aircraft is area-ruled for supersonic wave drag design. And we're not sure, talking actually to the British, I have consulted with the British a little bit on this with their new Bloodhound design. They believe that that's not a very important rule to gauge for ground when you're in proximity of ground. But it is a consideration, and we have to look at that. Ground proximity, dirt ingestion into the engine, we have to watch out for that. Any kind of structural interactions or resonating of the structures as we increase in speed. Stability and performance, we're looking at, of course, the thrust and drag requirements. We definitely have to have enough thrust to push through the drag. And then the canard actuations, you'll see in some of the images we have a canard on the front of the fuselage that balance the load, the aerodynamic loads, and try to give us a constant lift, I guess, as we increase speed down the track. And of course we're looking at body lift and balances. So CG of the airplane, or the car should I say, is important, and the contact points and where the wheels contact the surface. So aerodynamic improvements, of course, we'll have wheels and struts and all kinds of axles sticking out, so we need to put fairings over them and design it in a way such that we have enough thrust to push through the drag. So, whoops, a little lagging here. A large challenge is to design a fairing system around the suspension system in a way that keeps the drag at low enough levels to achieve our goal, with the available thrust while keeping the car on the ground with a safe stability control characteristics. The image shows a first cut of a fairing design around the aft suspension system and parachute cans. This area here. Important boundary conditions like modeling the inlet mass flow and thrust effects are modeled in this simulation. The car weighs about 13,700 pounds, and on the desert the wheel sinks into the playa anywhere from a half an inch to 2 inches, depending on the surface hardness. So actually the wheels sink into the dirt, and that is I modeled it as 1 inch below the ground plane. Three-dimensional Navier-Stokes simulations are run in steady state using CFD++'s Metacomps Mentor shear stress transport model. Full model with approximately 30 million cells is used for running crosswind cases, while half model cases are used for symmetric analysis. The primary tools I used to generate the fairing designs were Pointwise's database generation tools, and that consisted primarily of planes, database curves, Kuhn surfaces, the revolve tool, and the intersecting using curves and surface tools. It's a pretty powerful suite of basically some CAD tools, which is what I like. The flexibility to control points in and around the car is critical to resolve the flow features. As you can see here, I use multiple domains on the ground plane to cluster points underneath the car to produce a finer mesh for shock capturing. So after generating the volume mesh around the car, I use some of the quality checks, such as the max min included angles examination tool, image up here on your upper left, to locate potential areas of poor quality meshing, possibly giving the flow solver troubles. So the image in the upper right-hand corner of this chart shows a cut plane for maximum included angles through the suspension fairings. One neat feature of the tool is that the values are displayed over here in the legend as a cursor moves across the cells. And also note that the well-defined prism layers extending normal to the surfaces, the viscous layers. Another tool is the glyph scripting tool. And I'll play a little movie here that will show, the glyph can produce scripts for repetitive grid processing. For example, I don't know if it's being shown or not. I don't see it.
Yeah, it was just playing at the beginning there, Darren, so it kind of looped through while you were talking about the meshing.
Oh, okay. So, for example, I use scripting to perform canard angle studies. The script reads in a baseline grid, rotates the canard about a prescribed axis, and then updates the domains automatically, and exports the new grid ready for the flow solver. And I still don't see the movie, but the movie was supposed to demonstrate how the surface mesh automatically updates around the canard as it sweeps through a prescribed motion.
It did, and we were able to watch that while you were talking before. So
oh, was it that quick?
Yeah,
Sorry,
it just did loop. So that's okay.
All right.
The rest of us saw it. We're good.
Sounds good. Let's see here. So the two graphs show some of the automated post-processing capabilities. The upper graph shows the accumulated drag force along the vehicle's body for both pressure and shear contributions. This graph helps to identify areas of the car that contribute the most drag and that could be improved via redesign work. And as you can see that most of the drag is increased in around the aft suspension system where the axle sticks out. The lower graph to the right shows the lift produced on each individual part of the car, like the body, canards, fairings, parachute, etc. Again, this graph gives details about the car's surfaces producing the most downforce or upforce that can help drive the design of the car aerodynamics and structures. And Kevin Colburn will discuss these kinds of charts in a more detailed later on in the presentation. So here we are. So this chart shows the results of the fairing design cycle 1. The plot is of a force versus speed of the car and shows both lift and drag forces here and here. So also plotted here is the max thrust available line, which in our case the engine can produce max thrust of 18,500 pounds, and also a constant weight of the car. So the objective here is we want to look at the lift and make sure that the car doesn't come off the ground, and it would if it reached 13,700 pounds. And also looking at the drag polar. Of course, our goal out here with the dotted lines are this dotted line here is what we would need to actually break the current world record, but our goal is to get to 800 miles per hour. And you clearly see that with this design 1, it doesn't reach that. So so essentially we would have to go back to redesign. So starting with the green line, the triangles, the curve at about 680 miles per hour crosses the max thrust line. That's the max speed we could reach with this design. Also, one thing to note is on the lift, as we increase in speed, the aerodynamics pushes down on the car, driving the car into the ground essentially. Around 450 miles per hour, it reverses and the car starts producing an upward lifting force and reaches its max lifting force around 11,000 pounds at 700 miles per hour, and then drops back off. Now, this will, the drop-off is really due to movement in shocks and pressures around the car. And the two additional lines that I have on here are related to ground plane effects. So the black lines represent lift and drag for the car with no ground plane, and then by adding the ground plane, it will be the upper blue line here and the lower light blue line here. And so the overall effect is when we add ground plane with increasing speed, the drag actually increases and the lift, I guess the downforce, increases on the car. So it does have a dramatic effect. So we recently tested the car at the Alvord Desert, and that's located in the southeast part of Oregon, approximated at the red dot on the upper right-hand corner of the chart here. So the desert is located about 4,000 feet in altitude, and the primary test objectives were to collect pressure data at 16 locations on the car surfaces, indicated by the image on the lower left. And also 2 was to collect acceleration, deceleration, and rolling resistance data to use in our time, speed, distance calculations. We were able to collect rolling resistance, the drag that the wheels produce with contact on the ground. The force was measured at approximately 900 pounds. So this means that we have 900 pounds of thrust we cannot use to push the car through the aerodynamic drag. And unfortunately, during our third test run, the right-hand magnetic brake rotor failed, and we had to stop testing. And I can't show any data today because it's still being processed and looked at. So I apologize for that. Some people may want to see it compared to CFD data. So my last chart here basically shows the aerodynamics of the car as we tested in the Alvord Desert. So prior to Alvord testing, CFD simulations were completed on the model that closely approximated the car. Here's a plot of total lift and drag versus speed. Our goal for the Alvord Desert was to get the car up to but not to exceed 600 miles per hour. Again, this was to collect data to compare to CFD modeling to build our confidence that we are capturing the aerodynamic effects around the car correctly. So the graph shows a slight downforce on the car with increasing speed up to 500 miles per hour. Then starts to lessen to move to a more neutral force at 650. So right around this point here, the car would have the same, would be 13,700 pounds static weight on the ground. And I wanted to look at the stability and control analysis are also complete. So I thank you for listening. I will now turn the meeting over to Kevin Colburn to discuss more about the use of Insight and the scripting on this project.
Just hold on 1 second. We're having some technical difficulty here. Okay, I'll now turn things over to Kevin, so go ahead, Kevin.
Okay, thanks, Chris and Darren. My name is Kevin Colburn. I'm going to talk a little bit more about how we've utilized Python-based automatic post-processing within Insight for the North American Eagle project. So let me see here. There we go. So to give you a bit of a background, you have from sort of an option of doing scripting that is sort of quick and robust. This is kind of old school scripting. It's very robust, but it's also fairly complicated and relatively inflexible. And typically users had to dive deep into the scripting language, have a lot of knowledge of how the script works, and potentially programming in order to make something like that work. So that was a bit too difficult to use in this sort of situation. And really what I wanted to do was to simplify for the user the control of the scripting and of the post-processing. So from a very high level, kind of orchestrate how things work. So we developed this method of scripting via Python, which really allows you to adjust only the key items and not ever have to adjust the script. So the user can stay at a much higher level above the actual running of the script and go through and still control and look at the automatic post-processing. So we utilize Python here, and the reason why we do that is that we can abstract out and allow Python to make decision-based programming that allows the actual script to be very flexible, be very generic, and still be very powerful in post-processing the runs. So what does this look like in terms of a framework? We have the user starts out by doing sort of normal post-processing. He goes through the process as he would normally, and he just saves out the journal language in Python. From there, we actually abstract out the different key items. So for example, we would abstract out the variable names or the variable ranges, perhaps the number of images or the views and so forth, and abstract that information out so that that can be instructed in a smart way through Python. The final thing that we do is actually pull out and abstract the parts that were used, and this makes it very generic from case to case, whether the parts change, whether you have different configurations, whether in one case you might have a canard but in another case not. Maybe you have some additional appendages on the model in certain configurations, and you don't want to have to change the scripting in order to be flexible for generic geometries. Finally, we actually take the inclusion of external boundary files or part information from perhaps the solver. So Python can read external files in to take instructions from there in terms of how to interact with the model. And from a user's perspective, all the user is really doing is sitting and utilizing what we call sort of a header control file. This requires no editing of the actual scripts, and this header file is very generic and very powerful to instruct Python on how to do things from here on out. So kind of like a conductor in an orchestra. You really don't want to be musicians and actually play the instruments, but you actually want to conduct how everything else takes place. So this is an example of that header file. Up here in the top right, you see that we've got specifications of, for example, title or resolution, or maybe some things that you'd want to change from case to case. Down here in the center, we actually are able to control the section cuts that we're going to make through the model. So in this case here, we're specifying that we want X clips. We want to start at -1 and go to 56 in sort of units. And we want 51 frames. So there'll be 51 frames in X between -1 and 56. And then down here at the bottom is our actual logic to control which routines are going to be run. So we have these different libraries of routines that we can run and ask Nsight to perform on this model. And we can control things like the ranges for the clips of the velocity magnitude. So this will be the velocity magnitude range. It will go from -1 to 1.3 in the legend, for example. Or we want to do an isosurface, and here's the isosurface range that we want to use in this case. So from this is the only real interaction that the user has to have to control this Python-based scripting. And then he just really hits the go button each time. So this can actually be done tied into the solver, but the user could go through here, change a few values, hit the go button again, and off and running, and he'll get a whole new set of images and so forth automatically generated out. Now in terms of customization, this is an example of customizing Nsight further with Python. Here we have a graph of the accumulated drag going down the vehicle. We also have over here on the left some pie charts based off from the shear and pressure drag, so that we get a very quick look at the makeup of the, in this case, the drag, as well as a generic table over here on the right of all the forces. So in this case here, we're reporting out pressure and shear drag, as well as normalizing it. And this is all done generically, and this is all done based off from the Python being able to make decisions as we go through the model and populate something that's very generic. So what does this look like as a final output? This is an example of the output from Nsight. This is a movie file that's generated from Nsight. And this movie file goes through and gives you a very quick overview of the results of the model, what is actually being run, and it allows the user to kind of see the main changes from case to case. And this whole routine is controlled with that single header file. So looking at forces here, looking at CP profiles as well down the device. In a second here, we'll go through section cuts as we go down the model here as well. The ranges here on the bottom are controlled in that header file, so if you want to adjust the ranges, you simply change the range in the header file and re-execute, and all the information is updated again automatically. And so this is a quick way of looking at the results. It allows an engineer to stay at a very high level, to inspect the results, make sure everything looks good as expected, or highlight areas that need further post-processing or further analysis. But to keep the user out of the low level of actually doing all the hard post-processing, and let the Python scripting take over and do all that for you. So with that, I'll pass back to Chris here, and he'll finish up.
All right, thanks a lot, Kevin. That was really interesting. Thanks to Garen for your time. So yeah, before I just kind of sign off here, or actually we're not going to sign off, we're going to open up the floor to questions. I forgot to kind of talk about that a little bit at the beginning. So we're ready to open up the floor to questions. What you can do is you can type your question into the question panel, and what I'll do is I will do my best to read them off, and then I'll assign it to the appropriate person. So if you have a question about point-wise, again, I'll do my best to answer it, or maybe it's something specific that Darren can answer about his use of it. And specific about the project, feel free to go ahead and ask Darren those questions. And then if there's something specific about Insight, we have Kevin here as well. So go ahead and you can submit your questions into the Q&A panel on your GoToWebinar control panel, and I'll do my best. So I'll let you people go ahead and ask some questions. I'm just going to talk a little bit about the what can you expect from us from beyond here. So again, I appreciate taking your time out to learn a little bit about the NAE project and all the great volunteer work that Darren and the team are doing on that. It's just amazing to me that that this can be done on a volunteer time. So definitely kudos to them. So recording this webinar will be available on our respective websites tomorrow, both ours as well as Insight's, or excuse me, CEI's. And if you have any questions about Pointwise, again, you can go ahead and email me or call me offline. If you got specific questions about Insight, go ahead and contact Kevin, email him or give him a call. Or if you have questions about activities of the North American NATO project, or even wanting to participate, go ahead and contact Darren at the email address shown on the last slide here. So with that, I'll look at the Q&A panel and see if there's any questions that need some answering. Okay, so we have a question from Jeff Wen. He says, can you say more about compressing the cells from 30 million down to 15 million? So I think it's specifically about Pointwise. I'll answer that one directly. So I think what Jeff is referring to is the reduction in number of cells. So I mentioned that T-Rex is a TET only measure, so all the cells, including the boundary layer cells, are TET cells. And then how did I get to the 15 million? Well, in the boundary layer, in the viscous region, we have these high aspect ratio TETs. Now, if maybe the best way to think about this is in the reverse. If you take a prism, you can cut a prism up into 3 TETs. So if you have a high aspect ratio prism, so kind of the triangle is large but the height is small, you could split that up into 3 high aspect ratio TETs. So what we're doing is the converse. We have these high aspect ratio TETs to begin with, and we're going to combine them into back into prisms. So that's a 3-to-1 change in number of cells. So in a perfect world, it would go from 3 to 1, so we'd have a 67% reduction in cells. So first of all, for real cases like the NAE car, that's not going to happen. You're going to get somewhat closer, and it's only the viscous cells that can recombine. So in practice, you see what Darren was able to achieve, somewhere in the 50 to 55% reduction in number of cells. So that's why it just happened to be kind of 2 to 1 in this case. So good question, Jeff. So this question will be for Kevin. So I'll read off the question and I'll let Kevin answer it. It's about post-processing and Insight. So the question from Randy Hessel is it correct that the base Python code had to be written once, then the header file manipulates the base code like a typical input file? So go ahead, Kevin.
Yes, that is correct. Yeah, you write the base Python file once, and the base Python file actually comes from an original journal command from a live interaction with Insight. So you write the base Python file once, and you abstract out in there the different things you want to change, potentially change, like variable names, ranges, image counts, and so forth. And once you abstract that out, just stick that into the header file. And then as the Python is executed at the top of the Python, I basically read the header file, which takes the instructions from there and then executes from then on down through with logical decisions as we go through. So yeah, you write the base Python once, and that comes from a journal file, and then it reads the header file from there on out. So the goal is that the end user doesn't have to modify the script itself, and he only really has to orchestrate through the header file only from there.
Okay, so just Randy has a follow-on to that, and I'll kind of paraphrase what I think he's asking. Is the user responsible for writing the base code, or is this something that's provided part of Insight?
It's an open-ended question. So if the user wanted to write it, he's more than capable to do so. But If the user either doesn't have the time or skill to do that, CI would be more than happy to do that for you. So either or.
Okay, we got a one quick follow-on question from Jeff Wayne again about the prism recombination. He said, "Is this automatically done by pointwise?" Yes, it is automatically done, but again, I'll just reiterate what I think I was trying to describe earlier, was that this is automatically done only when you go to export the grid to your chosen format. Okay, do we have any more questions? Possibly we have some questions. Okay, we got a question from Paul Westhoff. I think this is a good one for Darren to answer. Darren, I've unmuted you so you can answer this one. Read off the question. He says, what is the runtime for and the post-processing time for the 30 million cell mesh?
Good question. So originally, the Lenovo company had dedicated a box here at home, and I had things running at home, but I could only run a half model case, which is about 15 million cells max with 48 gigabytes of RAM, and that was taking about 19 hours to get one solution back. So Cray Incorporate down in California allowed us to run on their Cray system, and so that helped me get full models through for crosswind analysis. And I run on 512 nodes basically, and I can get a full converged solution back, which is about 2,000 iterations in about 2 hours. Nice. on a 30 million cell grid.
Good question. I should also, I know that both neither Metacomp nor Korea is actually, I mean, obviously not participating in this webinar, but I think we should definitely give a thanks to Metacomp and Cray for helping out with that as well.
Yeah, so I'll throw out a little pitch here on the team. I mean, this is an all-volunteer team, and a lot of the, such as Pointwise and CEI, have participated in it, allowing us to use the software and basically helping out. So, I mean, kudos to you guys too. We couldn't do it without you, and anybody who, you know, out there can donate some of their resources and things like that. That's what kind of is helping us through bringing the title back to America. So, you know, Metacomp, Cray have all, you know, graciously donated some of their software tools and time on their machines to help us through this. There again, if anybody out there has a specialty in structural engineering, mechanical engineering, if you want to try to participate in a team environment, give me a call, let me know.
All right, thanks, Darren.
We're looking for communication specialist, anybody with networking experience, because, you know, when we go out to the desert, we want to, we have to, and we do, we have systems already set up for it, but we're always looking for people with you know, experience and have a different perspective on ideas. Yep.
Okay, I got another follow-on question from Paul. I think maybe I misunderstood his first question. He was actually asking specifically, what about the post-processing time with Insight?
So once I get my solution files, I mean, post-processing with Insight is a breeze. Essentially, once you get the files on your machine, I run the script, and it takes about, just on my home PC running Windows 7, it takes approximately 5 minutes to run through a lot of the scripts. Like Kevin showed, you can choose and pick. Maybe each time I don't need to run the velocity magnitude, so you can turn that library off. I typically look at the CPs, the accumulated force and drag and lift plots, and you know, isosurfaces for looking at separated flows and things like that. Very powerful. But you can, if you run all the routines, I think it's about, I'd say about 8 minutes probably to run through all the routines and spit out all the images. Good.
Thanks, Darren. Just a quick question here from Pratap. He just mentioned he just joined the meeting a little bit late. He said, when can we expect a recorded webinar? I think the information is here on the slide that's showing on the screen. So once we're done here, we'll have a recording of the webinar, and then we'll upload it and have it available tomorrow, at least on our website, and Kevin, what are your guys' time frame for having up on your website? Within a couple
Yeah,
of
I
days?
would anticipate it being up either tomorrow or the next day. So.
Okay, yeah, so per tab. So it should be on our website definitely by tomorrow, and probably the same for Insights or CEI's website as well. Okay, we got maybe about 10 minutes left before we probably need to sign off. Is there any more questions we have for either myself, Darren, or Kevin? Very good question from Jeff Wen. Do we have a website for the North American project? Yeah, actually, that's probably my fault for not including that in the first place. Yeah, I'll go ahead and answer this one real quick, Darren, since I've been to it several times. It's really easy to remember. It's www.landspeed.com.
Yeah, it's at the bottom of that page there in the middle, in the logo of the North American Eagle.
The logo of North American.
Ah, very good. Good eye, Kevin. Yeah, there it is. Yep. So landspeed.com, that's where it's at. So there's lots of, I've been to the website lots, there's lots of interesting pictures from just ongoing work, all the people involved. There's some bios on the major team members and some progress updates, and that's where you can.
We usually put like weekly, when we work on the car on the weekend, we'll put images up and what's kind of going on with the project. But the website is going through a redesign, so you'll see the new version of the website, and it will have links to some of the older version, HTML files. But yep, it's all there.
Good. So we got any more questions from the audience here before we sign off? I'll give it another minute or so here, and if we don't get any more questions, then we'll sign off. And I'll just say thanks again to Darren and Kevin, in particular Darren. Since this is a volunteer thing, this is outside his normal job, that putting in the time to help out putting this webinar together. I think it was really interesting. This is a really cool project to be involved with. So thanks, Darren, and thanks, Kevin.
You're welcome. Thank you.
All right, I don't see any more questions. So again, I want to thank everybody for attending, and look to both of our respective websites in the future for some future webinars. So thanks again, everybody, for your time.